In this video tutorial, I'll be updating my linear buckling example using ANSYS Workbench Release 2019 R2. Now, this is a simple slender bar of a square cross section, and it's 2.5 meters tall, and there's a compressive load at the top, and we're going to model it as a half symmetric model and fully fix the bottom end of the half symmetric part and apply our load as a free point at the top. Now the material properties are for steel, 207,000 megapascals for Young's modulus, and the properties for the cross section for 12.5 times 12.5 millimeter breadth and depth or width of this bar. The area and the second moment of area can be calculated easily. We will start our modeling with a static structural model, so we'll drop that in our project schematic and create our geometry. Now this will be a 3D geometry in Design Modeler. In Design Modeler, we can create our beam problem. This is going to be a beam type model. We can create, for example, on the XY plane, a simple sketch of a single line, and that will then be meshed with beam elements. So we are on the sketch. We can view the sketch from the front. We can zoom in to a realistic scale like 1 meter for this length scale. So then add our line. So we'll start from the center and move up on the y-axis. So we'll need to add a dimension for that. So the vertical dimension for this line is going to be from, say, this point to this point is going to be 1.25 meters. So we can fit view, and this is the sketch, and what we need to do is to create a concept of a line body. So we can create that from lines from sketches on the concept tool, and that's going to be based on the first sketch, and click on apply, and that's going to create our line once we create generate. So that will be one part with one body, and we need to specify a cross section on this one. So that can be done under concept, cross section, rectangular, and the dimensions of the rectangular cross section is 0.0125. That's for 12.5 millimeters, and the same in the H direction as well, 0.0125. So the properties of this cross-sectional area is also reported here, and that can be sort of compared with your hand calculation. And what we need to do is go back to our line body and then assign this cross section to it. So we'll just go and select rectangle one. And another important point is to be able to view these cross-section geometries. So if you go to view and then cross-section solids, we'll need to then rotate our model, and we can see that ANSYS shows this line body as if it's a 3D solid. So that is always useful to check that the properties you've entered, especially for your cross section, are accurate. Sometimes students tend to enter incorrect units, so instead of meters they are entered in millimeters, so the cross section and the line body dimensions don't match. So that's an important point. Now we can move to mechanical and apply our static load, which will then feed into our linear buckling analysis. Now I have started mechanical from the workbench project schematic, and the geometry is transferred from design modeler as a line body, and I can see that structural steel is assigned by default. The cross section is already defined as we've done in design modeler. The mesh needs a sizing control, so we can say on this line, first we need to select a line filter and select the line, and on this line we want either element size or number of divisions. So let's say we want to create 10 divisions, so therefore 10 elements along that line. So we can go to the mesh and then click on generate, and that will create our beam elements. So these are going to be beam 188 elements when the model is run in mechanical APDL in the background. So okay, we got the mesh. In terms of our static structural solution, we need to apply a couple of boundary conditions. We need to fix the bottom, so click on the point filter and click on this vertex and then click on apply. So that's going to be fully fixed, and we also want to apply a unit load at the top point of this line. So the 1 Newton load in the negative y direction, we can apply it as a component rather than a vector if you want. So it's going to be minus 1 newtons. So that load will create a compressive stress on this beam. That will then create our results, which will go into our buckling problem. We can look at total deformation. The stress results aren't calculated for the beam elements by default. Typically you'll need to use a beam tool. So the beam tool will have direct stress, minimum, maximum combined stress, etc. However, it's useful to be able to plot directly the stress and strain, etc. So under solution, click on beam section results and change that to yes, and then you'll be able to add on the solution the direct stress. For example, the normal stress in the x-axis, so that will plot nicely on the 3D geometry. So if we solve this problem, we can see that the normal stress on the x-axis is minus 6,400 pascals. So that is because we applied 1 Newton load vertically, and the cross-section area was about 152 millimeters square. So 1 divided by that will give us in terms of megapascals 0.0064, etc. So we can change our units just to make sure. We can go to home, units, and change to kilograms Newton seconds, and so our stress on this body is a compressive 0.0064 megapascals. So that stress result will now go into the linear buckling problem. An important point to note here is that the normal stress, which is the x-axis, is actually on the element coordinate system. So it's the elements x-axis rather than the global Cartesian coordinate system's x-axis. So this stress in the actual direction of the beam. The other beam tool results, direct stress is the same, and combined stresses will be the same, so there is no bending result. If there was some bending on this one, then it will have a different result. So total deformation is a very small number. It's a millionth or something like that of a millimeter. So what we can do is we can increase this force indefinitely. We can apply 1,000,000 newtons on this very slender bar, and we will not be able to buckle this structure because it's a linear static analysis, and there is no say imperfections or material or other nonlinearities in here that will start a buckling. The geometry is perfect, and the loading is also perfectly applied on the center line of this beam. So therefore, it's almost impossible to start a buckling doing a basic static structural analysis. And in the future, you could try to apply some imperfections like shape imperfections or slightly offset loads, or change to a different elastic plastic material type, etc., and then that will become a more complex nonlinear buckling analysis. But in this example, we'll keep it in straightforward, just a linear elastic buckling problem. We have completed the static structural analysis, and we are now going to the next step, which is running the buckling problem. So it's the eigenvalue buckling analysis system, and we'll need to drop it under cell A6 on the solution. So that will link the solution of the static structural analysis into our eigenvalue buckling problem. And we can go and edit the setup, and that starts Workbench Mechanical, and you can see that it's the continuation of our static structural problem followed by an eigenvalue buckling problem. Now the analysis settings will have a maximum number of modes to find. By default it's 2, we can increase that to 4 to see if there's a number of modes we can check. And the solutions are simply total deformations for the different modes. So we can look at mode 1 and mode 2, mode 3, mode 4, etc. So the 4 total deformation tools, and we can change the modes on these ones. And this is mode 3, and this one is mode 4. So what's going to happen is the linear elastic analysis will be rerun, and the results of that will be transferred to the eigenvalue buckling, and the important result is the pre-stress that will feed into the buckling, linear buckling problem. So when we run our solution, let's say do the solution now, we can see that the solution for mode 1 is reporting that the multiplier is 642, and this is the total deformation. It's the mode shape, buckled mode shape, and we can animate that, and that's what will happen if we apply this much load vertically downwards. That will cause this beam to buckle into this shape. The second mode is similar, but then the beam is now buckling into XY plane. So the first one was the YZ plane, and the total deformation 3 is another buckling mode. So we can look at how this will work. Essentially, this is requiring a much larger load multiplier, 5780. So in order to buckle the beam into this shape, it needs to be constrained more or less at the top, so it doesn't move, but then the force will move it into this shape in its buckling mode into the two planes. In this problem, another point I want to make is that this 642 um, is dependent on the material properties. So 642 is a load multiplier because we have applied -1 newtons. The load that will buckle this beam is minus 642 newtons. Now, if we wanted to change the material property and use a different material, how can we do that? So just a quick demonstration on applying a different material type. So first we need to go to our project schematic. In our project schematic, we can go to engineering data, double click on it, and that opens up the outline of the engineering data. And structural steel is the material that we used in our model. If we click on engineering data sources, that will list a number of different materials. For example, under general materials, you can find that there is a range of interesting materials, like from aluminiums, concretes, coppers, and that's the structural steel that we've used. If we wanted to use, say, aluminium, we could click on the plus sign, and that adds this book symbol next to this line on the C4 cell, and that means this is going to be available in my model as an additional material property. What I can also do is create my own material library. So there's a range of material libraries from geomechanical materials, composites, hyperelastic materials such as rubbers, etc. And I can create my own material library. I can say, say tools materials, and I can define a material library, for example, under a new folder called material, and select that folder, and I can give it name like tools material. So that is now in edit mode. On the column B, you can see that this is an edit symbol and this is checked, so I can define a new material. So I can define my own version of steel, say call it steel 1, and it says a question mark because there is no properties defined yet. We can go onto the toolbox and double click on isotropic elasticity, and we can add the material properties in here. So Young's modulus we can enter as say 207,000, Poisson ratio 0.3, and that is the minimum that I need for my material. And I can add other properties such as physical properties like density, and I can define that value in terms of say tons per millimeter cube or kilograms per meter cube. So 7,850, let's say, kilograms per meter cube. So these materials will then be available in my model. Before they are, I'll need to make sure that this tick box is unchecked. So it will ask me, do you want to save the modifications to the library? I'll just say yes, and that material library is now saved for my use. So I can now go back to my engineering project schematic, and if I say go back to my model, it requires the material information to be reread. Just say yes to that, and when we go to materials, we can see what materials are available. So at the moment it's structural steel and aluminium alloy. I need to add my own version of steel as well. So to do that, I need to go back to my engineering data and make sure that engineering data sources, tools, materials, and the steel 1, this is checked, so that's added to my project. So that symbol means that it's used in my project. So going back to my setup, and that's going to be, by default, it's got structural steel assigned to it. I can change that to aluminium alloy or steel 1. So if I use steel 1 and rerun my model, what you will find is that the load multipliers are now slightly higher, 665. So we can change the material to aluminium, which is essentially a lower Young's modulus for the material. So if you go to line body and change that to aluminium, and then again rerun it, what we'll find is that the load multiplier is much reduced, a third almost, 228. So minus 228 newtons in the y direction will buckle this beam if this is a structure made of an aluminium alloy. So this concludes the tutorial on the linear buckling of a simple beam structure.